And welcome back. As we continue our cosmic journey, let's go ahead and get ready to look at the Earth and the sky around it. Now, in order for us to do that, we need to first start by creating a map of our world and beyond. So, pretend for a moment you are a map maker, and we want to create an accurate map of our cosmos. Well, we need a way to identify the location of all the major features on that map. If we think about this in either, let's say, a handheld map, whether it's digital or paper, this is typically done through things like cities or natural landmarks such as lakes or rivers. So very similarly, if you're an astronomical map maker, you need to find ways to identify the location of stars, maybe galaxies, or other celestial objects. On Earth, our maps are pretty easy for us to do because we can divide the surface of the Earth into a grid, and each location on that grid can easily be found using latitude and longitude. So astronomers actually are going to apply a very similar system here for objects that we can see from Earth in the sky. Now, learning about these different approaches can help us understand the apparent motion of objects in the sky from various places on Earth. So let's actually start locating some places on Earth. How would we do this on Earth? And then we can apply that to our stars. Well, on Earth, Earth's axis of rotation defines the locations of its north and south poles and also the equator. East, which of course is the direction that the Earth rotates, and west are defined by the Earth's motions. At almost any point on Earth, the four directions are well defined, even though our planet is round rather than flat. Our maps are pretty flat because they're relatively two-dimensional. But again, we think about we're trying to put a two-dimensional surface onto a three-dimensional plane. But we can use these ideas that we have of latitude and longitude to find a system of coordinates that are attached to our planet. Coordinates on a sphere are a little bit more complicated than those on a flat surface. So we have to actually define circles on the sphere that actually play the same role as a rectangular grid that you would normally see on maps. So let's divide up this globe. And the way we do this is we have great circles. And what's a great circle? Well, a great circle is simply just any circle on the surface of a sphere whose center is at the center of the sphere. So in other words, it has to pass through the very middle. Now, Earth's equator is technically a great circle on Earth's surface because it is halfway between the north and south poles, and the center of that circle would lie, of course, at the Earth's core. We can also imagine a series of great circles called meridians that pass through both the north and south poles and are perpendicular to the equator, crossing it at right angles. Any point on the surface of Earth will have a meridian passing through it. Now, the meridian simply specifies the east-west location, or the longitude of the place. Longitude is defined as the number of degrees of arc along the equator between your meridian and the one passing through Greenwich, England, which has been designated as the prime meridian. If we look at the prime meridian, it has a longitude value of 0 because that's effectively our starting point. Now, longitudes are measured either to the east or to the west of the Greenwich meridian, going from 0 to 180 degrees. And again, if we look at latitude and longitude, we can use it to kind of help us make coordinates here. Our latitude is our north-south location, or the number of degrees of arc you are away from the equator along the meridian. Latitudes are measured either north or south of the equator from 0 to 90 degrees. And again, because latitude is the number of degrees north or south of the equator, and the longitude is the number of degrees east or west of the prime meridian, it allows us to really find a way to get a nice coordinate map here. And we can use this to find cities such as like Washington, D.C. very easily on a globe. For example, D.C.'s coordinates are 38 degrees north and 77 degrees west. So let's take this same principle of using kind of a grid system to help us locate places in the sky. So positions in the sky are measured in a way that's very similar to the way we measure positions on the surface of the Earth. But we don't have latitude and longitude. Instead, we use coordinates called declination and right ascension. So to denote positions of objects in the sky, it's often convenient to make use of the fictitious celestial sphere. Remember, the celestial sphere, we talked about, it was a way ancient astronomers kind of looked at the sky and divided it up into different sections, and they said, okay, well, here's the Earth. And they said, well, the sky appears to rotate around different points of the sky. We have the north celestial pole and the south celestial pole. And halfway between those poles, and therefore 90 degrees from each pole, is our celestial equator, which is a great circle on our celestial sphere that is in the same plane as Earth's equator. Therefore, if we can take those things, we can actually use markers in the sky to set up a system of celestial coordinates using our declination and right ascension. So, with declination and right ascension, declination is measured the same way that latitude is measured on the sphere of Earth. We start from the celestial equator toward the north, or the positive direction, or south, which is our negative direction. So Polaris, the star near the north celestial pole, has a declination of almost plus 90 degrees. Similarly, if you were to head down towards the south pole, obviously we don't have the necessary south star, but if you were to follow that same direction, you would of course be moving towards a negative 90 degrees. Now, right ascension, RA, is very much like longitude, with the arbitrarily chosen point where we start counting is the vernal equinox, a point in the sky where the ecliptic crosses the celestial equator. Now, right ascension can be expressed either in degrees or in units of time. And this is because the celestial sphere appears to turn around the Earth once a day as our planet turns on its axis. Therefore, our 360 degrees of right ascension that it takes to go once around the celestial sphere can just as well be set equal to 24 hours, and each 15 degree of arc is equal, therefore, to 1 hour of time. So let's keep this in mind as we start talking about the turning Earth. We might ask back to this very basic question. Why do many stars seem to rise and set each night? So why, in other words, does the night sky seem to turn? Well, the two explanations are either the rotation of the celestial sphere could be accounted for either by a daily rotation of the sky around a stationary Earth, or by rotation of the Earth itself. Now, of course, we know that it is the rotation of the Earth, but this has also been proven by French physicist Jean Faucel, who provided a ambiguous demonstration of this demonstration. And what he found out is that as the Earth turns, the plane of oscillation of the pendulum, as we can see here in this demonstration picture, it's going to shift gradually so that more of the targets, which in this case are these kind of little wooden pegs that you see here along the edge of the table, they are knocked over in sequence just as this is moving through the course of the day as the Earth rotates.